All right, so today, Thursday, April 10, we'll take our quick peek at the calendar. Today we're going to cover two sections, 4.3 and 4.5. Normally we cover 1.5 sections. These sections are fairly short, so I think we'll be able to do 2 in one day. Next class is the due date for assignment 6, which means that we have a quiz coming up. So on Tuesday coming up, it is quiz number 3. It is on all the stuff in the box that says quiz number 3 on that green sheet, okay? So it's just the last few sections, 2.9, 4.1, and 4.2, not the stuff that we are doing today. Stuff we are doing today is not on the quiz, all right? Yeah, finishing 4.1 and 4.2 is the homework. We're going to do 4.3 and 4.5 today, but that's not due until the day after the quiz, right? Other questions on the calendar? Okay, so let's jump in here on page 210. We're going to change things up a little bit here and talk about graphing. There's the normal spiel here about resources for quiz 3, but this reminds me, have I given you guys the yellow 3? No, I need to do that. I'll do that in a little bit today. But let's jump in here in the middle of this page with the objective. We'll go to Meg B. Oh, yeah, hold on one second. Yes, Meg. I wouldn't toss them, but you don't need to bring them to class every day. Yeah, for the rest of the semester, we're in blue 3. Good question. All right, Meg B, can you read the objective? Okay, so I think this will be a welcome change of direction for some of you. This is really quite different than the material we've been covering. We're just going to be plotting points, but instead of the points lying on a line, they're going to be on a curve. So can we go to Geneva for part A, number 1A?
To draw your graph over a guide, over the command shown. Draw your graph so that it ends reaching to the outside of the grid.
Okay, thank you. So let's see if we can give this a shot. We're trying to graph y equals 2x squared. It's the first time we're graphing something with a squared in it, different from the other stuff that we've been graphing. And we're going to begin with a table. So let's make our table here. X or y, which one goes in the first row? X. And then y in the second row. Now we have choices. You can put anything you want in the X, but we want to graph something on this particular piece of graph paper, and it looks like the X's range from -3 to 3. So how about we do those numbers in our table? -3, -2, -1, 0, 1, 2 is probably enough. And then let's see if we can plug in each of these numbers into the y equals 2x squared equation. So for example, if we plug in -3, which is our first x, then we're doing -3, so we'll write it this way, y is equal to 2 times -3 squared. Notice the parentheses around the -3. Is the first thing we do 2 times -3? What's the first thing we do? The exponent. So let's square that thing right there. -3 squared. Positive or -9? Positive 9. 2 times 9 is 18. So 18 goes right there below the -3. Okay, we've got like 5 or 6 other points to plug in. Can you guys divvy up that work at your groups? I don't need everybody doing 5 or 6 points. So just split it up, decide who's going to start on the left and who's going to start on the right, and then grab the numbers from each other, and finally plot those points. Okay, so we've got all these points, and now we're just going to plot them one at a time, and we know how to plot. Just be careful because the scales are different on the x and the y-axis. So for example, -3, 18. I go out here left to -3, and then we're trying to go up to 18. So maybe somewhere around there. Is that fair? And so we'll just put a point right up there at -3, 18. Go ahead and plot that point as well as the other 5 or 6, however many you have in your table. All right, So you guys should have 6 or 7 points plotted all together. And for the first time, again, we don't have points that lie on a straight line. There's a curve that connects these points, and you're just going to do your best job to connect them with some smooth curve. And so I'll try to hit my points with something like this. It's not going to be perfect, but if you are trying to graph an equation, you're trying to plot all the points, not just the 6 or 7 that you end up picking. So you do have to connect the dots. And connecting the dots earlier this semester meant straight line. Now it's not straight. We just get a curve. So apparently things with an x squared look kind of curvy, like this one does here. Okay, and yes, Meg. I made up those numbers looking at the x-axis on the graph paper. So like on the next page, I might pick different numbers because here the graph paper is -10 to 10. So I might pick like -10 and -6 and -2. You just want to pick ones that are spread out, but specific to the graph paper you're going to use. That's right. If the equation were something like x equals 2y squared, then you're right. The y-axis would kind of guide you there. Yeah, but I can tell you that this semester, it's always going to be a y equals something. Yes, let's do part B. So part B says use your graph to estimate the solutions to the equation 2x squared equals 12. Okay, so 2x squared should look familiar. I'm going to circle the 2x squared part and say, well, it's exactly the same as the 2x squared in the original equation, the y equals. And so I guess what we're saying is that 12 is playing the role of the y. You buy that? Like these two equations say exactly the same thing. It's just instead of a y, there's a 12. The equation's been reversed, but we can handle that. So what we're really saying is that the y that we're interested in is 12. So let's go to the y-axis and find 12, ballpark. So maybe somewhere around there. It's 12. And then we're going to take that y equals 12 and we're going to go straight to the right until we hit the curve. And then where are we going to go? Straight down. And this is a process that we've done before. We did it before when the graph was a diagonal line, but we can do the same process even when it's a curve. So you go straight to the right and then straight down. I guess I didn't go straight so well here. Let's try again. Yeah, maybe 2.5 for me. What's that? Yeah, and we're going to have different answers here because our curves are all going to be a little bit different. And I didn't use a straight edge here, so I could be more accurate if I had a straight edge. But there's a range of answers that's full credit for this kind of problem. And so we land down here on the x-axis. For me, I'm going to say 2.6. But you can say some other number, 2.5, 2.4, 2.3. There's a range. If you say 2, I'm going to say that's not it. I mean, like 2 is far away from the answer. Okay, so x equals 2.6 is an answer to that equation, roughly. Are there any other answers that still match up with this y equals 12? Yeah, there's a negative thing here happening. Here's another point on the curve where y is equal to 12. And again, we can go straight down. And it looks like for me, it's about negative 2.6. Again, you can have a different number. You get both. Yeah, you get both. So yeah, you have to do both sides because when we say solve an equation, we mean find all of the solutions to the equation. And in this case, there are 2. So the solutions to this equation are, for me, x equals 2.6 and x equals negative 2.6. So oftentimes this would be like a multi-part question, and the next part would say, make sure the answer to the previous question is an equation. And so that would be my way of reminding you I'm looking for x equals. Yeah. Okay, so that's it. So what's the right answer? Well, the right answer involves not using a graph. The right answer involves using pure algebra. We know how to solve that equation. We did it last class. So 2x squared equals 12. I'll just do it down here real quick. First thing to do is get that 2 out of the way by dividing both sides by 2. So that means that x squared is equal to 6. And if I see x squared, what do I do to it to get rid of that squared? Is the square root. So let's take the square root of both sides of this equation. And square root of 6, whatever that is, I'll get it on the calculator. But that's my answer. There was this one little detail that we talked about last class. I don't think it's the most important thing in the world, but I do think that this is not a complete answer. How many solutions did we find? We found 2, but this final thing is just the one. And so this little detail that we talked about last class was that when you take the square root of x squared, it's actually absolute value. Like I said, I don't think it's the most important thing. What is important is that you get 2 answers and not just the one. So our 2 answers are the square root of 6 and negative the square root of 6. And we'll just grab our calculator to get a decimal here to see how close we were. So my answer was 2.6. You might have something slightly different. So what do I do here? 6 and then the square root button. 2.45. Anybody close? 2.5 is close. 2.4 is close. 2.6 is, okay. That would have been better if I'd used a straight edge. All right, so that is it for the first demo. What you're going to do is this classwork here on the next page. It involves 2 different graphs and solving 2 equations. See if you can work through these kind of quickly as you make your tables, and then we'll come back together and play with these blocks. So yeah, if you've seen FOIL before, that's this. Oh, I see. Okay. All right, so let's have a look at the objective. We'll go back to Jen. Okay, so first a word that I don't know that we've really used before in this class. Maybe you've seen it. As a prefix, what does by mean? It means 2. Okay, so I'm just gonna look at this first match question. So by we know means 2. How about mono? Means 1. How about try? 3. And then down here also try, still 3. So apparently these prefixes tell you how many terms there are in the thing. So the first one says monomial. So do you see the thing over there, A, B, C, or D, which is 1 term, is B. So the answer to this first one is B, because it has just the 1 term. Where's the binomial over there with 2 terms? C. And so we've already taken care of B and C. How many terms are in the other 2 guys? 3. So each of those things is called a trinomial, and we just have to decide which one it is. And you can see there's like another word in front of trinomial for each of these options. Let's see, cubic and quadratic. So which one is which? Cubic is D. Cubic is A. So they both have 3 terms. Well, what does cubic remind you of? What number does cubic remind you of? It's 3, right? So like x cubed looks like that. So I'll just write equals x cubed. So the thing with an x cubed is the cubic trinomial. So which one is that? D. So this one here is D. And then I guess by process of elimination, the last one must be A. But here's the unfortunate part. We've been playing this prefix game. What does quad mean as a prefix? It means 4. But in math class, quad means x squared. I won't get into the historical of why that's true. There was a reason for that way back when. But unfortunately, quad does not mean 4 here. It means x squared. So, quadratic always refers to x squared. Okay, so let's take a look. I've got some pictures here, and we're first going to start in part A. And I'm going to remind you of the only algebra blocks that we need for this one. So I'm going to hold them up, but see if you guys can pull out of your bins there a whole bunch of these squares, yellow squares, not the big cubes, but just the square things. And you're also going to grab the yellow rods. and just pull out a bunch, and then a bunch of the little green cubes in the middle. Okay, so we want these three things here. You don't need to grab them all, just a pile. Okay, everybody's got them? They're in the back. You guys can put those yellow cubes back in. We're only going to be using the thinner square ones. Yeah. Okay. All right. So let's take a look. So part A says use the algebra tiles to build the rectangle circled in blue on the top left in the picture above. Now you guys don't have colors on yours, but top left is this one up here. So you're just going to use the pieces that we pulled out and just physically make one copy of that shape right there. Yeah. So we just need at least one copy. It's okay if you try to make more than one copy. Okay, and then put the green cubes in the blank spaces. Yeah, just like that. That's okay. Okay, everybody's got this picture in the top left? Okay, good, good. All right, next one. Excuse me, it says part B. What does first a reminder of the names. So the square looking thing, the yellow square looking thing, we're going to say it has a dimension of x on the one side and x on the other. And so if we're just looking at the area of the top thing, we know length times width, right? Because it's a square or rectangle. So x times x is x squared. So the area of the yellow square, top part, is x squared. The little green cube is the same thing, but its dimensions are 1 and 1. That's how we define it. So what's the area of that, the top of the green thing? Is 1 times 1, which is just 1. And then the yellow rods, the rectangular looking things, one dimension is x and the other dimension is 1, and multiply them and we get area of the front face here is x, okay? So whenever we refer to like an x squared, like here in part B, we're talking about the yellow square looking thing. All right, so part B, what does 3x squared look like with algebra tiles? So how could we make 3x squared with algebra tiles? What would we use and how many? 3 rods for x squared. So let me make clear the what I'm calling things. So I'm calling this guy the square, this guy's the rod, and I guess we can call this guy a cube or something. So how do I make 3x squared? The rods are x. Square and a rod? So that would be x squared and x. Okay, hold on. So I'm going to highlight some stuff here. These are the things that we are referring to. Whenever we try to name something, it's going to be those things inside the pictures, all right? So if we want x squareds, you have to use the square things. 3 of those square things. 3 of the square things. Just 3 of the square things. We can't use the green guys because the green guys are just ones. Right? So if I want 3x squared, I'm literally grabbing 3 of these squares, okay? What if I want 2x plus 1? Okay, which one of the shapes is x? Is the rods. So we're going to grab 2 of the rods plus a single green cube, okay? All right. Okay, is everybody okay with the 2x plus 1? 2 rods. Yes, so 2x plus 1 says you're going to grab 2 of the x's, 2 rods, plus 1, and the 1s are those green cubes. Okay, so in your groups, we're going to come down here to part C, which says, give a quadratic trinomial. Okay, so that's new vocabulary. We'll analyze it in a second. That represents the area of the algebra tiles circled in red on the right in the above picture. So what I want you to do is write down some expression with x squareds and x's and some other number that represents the combined area of all this stuff circled in red. So count some stuff, write your expression, and check your answers with your neighbors. Okay, how many x squareds do you see? 2. So 2x squared. How many yellow rods do you see? 7. So that's a 7 what? X. And then how many green cubes is 6, which is just 6. What symbols go in between if I'm looking for the total area of all that stuff? Pluses. So that right there represents the total area of the shapes in the top right. And can we double check that the words that we've used here are correct? Trinomial means what? 3 terms, and we see 3 terms listed there, separated by plus signs. Quadratic, unfortunately, doesn't mean 4. Quadratic means you're going to see an x squared someplace, and we do. Okay. Part D we've already done. We're moving on to part E. Find the length and width of the rectangle you made, the one that's sitting in on your tables. I want to know what's the length, meaning how far is it across the top, and what's the width, meaning how far is it down this way. So you're going to write some stuff with x's to find the length and the width, and check in with your neighbors on this one as well. About this. So this can be a little bit tricky for folks because we've just spent the last 5 minutes talking about these green highlighted numbers in the inside, the areas, but that's not what we're looking at now. We're looking at the lengths along the outside of the shapes. And so, for example, we can see that this length right here is x, this one right here is also x, this length is a 1. So it's the lengths that we're interested in right now, not the areas. So if I go from here to here, how long is that? That's just a 1. It's a little tiny length. How long is that? That's also 1. How long is this? That's what we're calling x, which is this distance right here. So if we want the length of the whole shape from here to here, I guess the width is what we called it before, it's x plus 2. That's it. And then now we'll go along the top. How long is this piece right here? That's x. And then here, another x. And then here is a 1, and a 1, and a 1. So all together, 2x plus 3 is the total distance along the top. Okay? All right, so now we're moving on to the next page. And we're going to try to bring 2 different ideas together. So here are the conclusions. How can we use the length of the width to get the area of the rectangle that's sitting on your page? How do you find the area of any rectangle? Is length times width. So we're going to multiply. What did we say was the length across the top? 2x plus 3. And what was the width along the side? X plus 2. I'm going to put each of them in parentheses because they were separate things, and we got to make sure we group them like their length and width. So we should believe that if we were able to multiply those 2 things together, we would find the area of the rectangle because it's length times width. Yes, Meg. We are about to learn how to multiply. We don't know how to multiply these at the moment, so we should be stuck at this stage. Yeah, but we don't know how to multiply those 2 things together. But going back to the previous page, just go back to the previous page, and I want you to compare the picture on the top right with all the algebra tiles separated from each other. I want you to compare those shapes to the ones that are sitting on your desk right now with the nice rectangle you made already. How did the shapes that are all separated in the top right picture compare to the nice rectangle that's on your table? They're exactly the same collection, right? You can count. You see 2 of the x squared tiles in the picture, and you see 2 in your rectangle. There's 6 of the green cubes in the picture and 6 on your table. So they're exactly the same. So that means that the area of the stuff circled in red here is exactly the same as the area of the stuff circled in blue. They're the same shape, just moved around, right? Area didn't change. But you already told me what the area of this stuff in red is. How many x squareds? 2x squareds plus 7x plus 6. We know what the area of that one is. So do you believe that the area of this nice rectangle is the same, 2x squared plus 7x plus 6? Why no? But it was the same shapes, right? So the area of all this stuff over here in red is just the sum of the areas of the individual pieces. And those individual pieces are exactly the same pieces as they are over here in this rectangle. So ignoring the length and width of the rectangle, this 2x plus 3 and the x plus 2, it's just exactly the same shapes moved around. So the area hasn't changed at all. So it's true. It's just spread apart, but the area didn't change. So the area of both of these collections is exactly the same. It's made up of the same pieces. So this 2x squared plus 7x plus 6, which was your area of the top right, is the same as this area in the top left. So moving here to part 2, it says, how does the area of the rectangle on your paper compare to, or on your desk compare to the area of the collection? Same. And so we're going to summarize as follows. The area of the collection we already wrote down. Can you remind me? 2x squared plus the collection. Was it 7x? Plus 6. That was the area of the collection. But up here in the top right of the board, we wrote down the area of the nice rectangle that you made on your paper, because it was the length of that rectangle times the width of that rectangle. Oopsies. X plus 2. And we said that the area when it's separated is exactly the same as the area when it's together. So here we have a brand new equation. Is that if we multiply these two binomials, we get this quadratic trinomial. So here's the deal. We don't need to go through. So Meg had a question. So how do we multiply when we see something like this? And I said, well, we don't know, and we're learning it right now. So apparently this is the answer. But gosh, I'd really like to be able to get there without busting out these algebra tiles and counting the blocks every time. So here's a procedure that we can do that will show us exactly how to multiply two things in parentheses like we have here. So starting from scratch, just looking at this 2x plus 3 times x plus 2. So we are now going to learn how to multiply these two guys together without referencing the blocks. Suppose that I temporarily just got rid of this 2x right here, and there was no parentheses there. So it just looks like that. 3 times x plus 2. You guys remember how to distribute that 3? 3 times what? 3 times x plus 3 times 2, right? And so I think we ended up, I'm not sure, I think we did this. I think I ended up kind of writing stuff like this, where it was like the 3 comes in and it hits both parts. Okay, so I could deal with it if it was just the 3. Well, what if it was just the 2x? What if this thing were sitting on the outside of the x plus 2? We know how to distribute that 2x in. 2x multiplies by x, and also 2x multiplies by 2. And so I'm going to draw up here at the top, 2x hits the x, 2x hits the 2. And so what we're going to do is just multiply. We now have 4 different multiplications we have to do, and then we'll add everything up at the end. So let's try it. First one is 2x times x. It's 2x squared. Next one is the 2x times 2. It's 4x. And you guys remember over the last couple classes, we did a lot of these kinds of things where we had to do stuff like 2x times 2 and get 4x. So all that is coming back. Like all those little problems are now part of a bigger problem. Next one we do is the 3 times x, 3x. And the last one we do is the 3 times the 2 is 6. That's true. First, what are the symbols that go in these blanks I've left? They're all pluses, because that's what the distributive law tells you. It says you multiply and then you add at the end. And then Geneva, can you say again? Like terms, which ones are they? Everyone agree we can mush those together and get 7x? Can we mush any other terms together? No. Okay, so did we get the same thing that we wrote up here? 2x squared plus 7x plus 6. We did. So without referencing the tiles anymore, this is how we multiply together two binomials. 2x plus 3 is a binomial. X plus 2 is another binomial. We multiply them together by doing this technique. And I think Sandy is the one that came up with this, but this reminded her of a lobster's claw. Can you guys kind of imagine a lobster claw like this? And so we're going to call this the lobster claw method, which just says you multiply, you just start drawing everything to everything, and looks like a lobster claw. Okay, so next piece of this puzzle. Doing this lobster claw gave us 4 terms originally. It combined down to 3 terms, but originally it was 4 terms right up there. I want to see where they show up in the rectangle that we built, which is back over here. So let's take a look at, I'm going to draw in some extra lines here. I'm going to draw this line right here and this line right here, which is my way of really separating the shapes that are on your table. You have 3 different kinds of shapes, right? I'm just separating them by drawing in those 2 lines. So looking at areas again, what's the area of this guy right here? Is 2, and remember the area of the squares are x squared. So this is a 2x squared, yes? Let's do this guy down here. What are each of these single ones? They're each x. So 4x is down here. Another color, let's go blue. Yeah, that's a 3x up there, right? Because you have 3 x's. And then the last one, I'll do red again. Yeah, what are each of these worth? These are each 1. And so altogether it's a 6. And do you see those 4 things when we did the lobster claw before we combined? Yeah, so the lobster claw is doing something that isn't just like this random, okay, do a lobster claw because it's cute, but it actually matches up with what we did on the tables. Okay, one final way to multiply these 2 guys together, again, without referencing the tiles. So I'm going to write this again here, this 2x plus 3 times the x plus 2. I'm going to show you a different way to get to the answer. And the way that I'm going to show you is called a rectangle diagram. So what we're going to do is start by drawing a rectangle. And then I'm going to draw some lines roughly through the middle. It doesn't much matter where you put them. You just need to have 4 spaces inside of your bigger rectangle. They don't have to be even. Okay, looking at the previous page, what was the length across the top of the rectangle? 2x plus 3? So I'm going to put that right up here. 2x, I'm going to put the plus sign right on top of that line that I drew, and then a 3 over there. And then what was the width? X plus 2. So I'm going to put that on the side. X, again, I'll put my plus sign right there on the line, and then a 2. Okay, focusing on just this rectangle right here. I'm going to write down the area of that rectangle. I'm going to do it by multiplying that 2x times this x. We're going to put the answer right there in the middle. 2x times x is 2x squared. Everybody see it? 2x times x. Now I'm going to look at this guy over here in the top right. And to get that one, I'm going to multiply 3 by something. What am I going to multiply 3 by? Is the x. So you just have to bring this one all the way across, and we get a 3x there. Can you guys do the same thing to fill in the bottom row? Just multiply, something from above by something from the left. So what's the bottom right? Just 6. That's good. Yeah. Okay, so those things, I think, I'll put it back to, you stay where you are, but I'll go back one page. Do those things agree with what we put right here in this picture? 2x squared, 3x, 4x, and 6. And you can get them by just multiplying like in a very natural way, right? Something down and something across. Okay, and so if I wanted to write down my answer to what do I get when I multiply these two guys using a rectangle diagram, I just copy the things that are inside this picture. 2x squared plus the 3x or the 4x, it doesn't matter which order you go in, plus the 6. You see the four pieces, and then we just add them all up. 2x squared plus 7x plus 6. So the new thing you need to get good at after today and after practice is multiplying things that look like this double parentheses. 2x plus 3, x plus 2. You have two choices, lobster claw, rectangle method. I'm never going to force you to use one over the other, but just get really good at one as opposed to being on both. Okay? Geneva. It's going to be on the next exam, but it's not on Tuesday's quiz. Okay. Yeah. Right. Nothing from today is on the quiz. Meg. Our review for the quiz is on Tuesday, so we will have like a. Yes. Yes. So so there's a long time between now and Tuesday, and I'm hoping that people spend a lot of time between now and Tuesday working on preparing for the quiz. Oh, that reminds me, I need to grab the yellow QEF things for people to practice. Yes. So you got people at your table, and I will come by and help as much as I possibly can on that Tuesday. But I'm hoping that stuff happens between now and then when you have more resources around you. Okay. Last thing, and then you guys are going to practice. But again, get really good at either the lobster claw or the rectangle method. You don't need to be really good at both. And then we'll just take a look at number 6 real quick. It says both of these methods can be generalized to other products. So for example, I'm just going to write this. We're not going to actually do it, but just to see that we could do it. This is different. The first thing in the parentheses, is it a binomial or a trinomial? Binomial, it's got two terms. In the second parentheses, trinomial. But the lobster claw and rectangle method both work. I'm just going to do the lobster claw method just to see that you could do it. This x has to multiply by what? By x squared, and also by the 4x, and also goes to everything. And then the 2, what does the 2 have to go with? All of them again. Right. So the idea here is that it's everybody in the first parentheses times everybody in the second parentheses. How many different multiplications have we just listed? 6. 6 of these little red curves. So you're going to end up with 6 terms out here. Some of them would combine, so it would get a little bit smaller. But the idea is that the lobster claw and rectangle method both generalize. Same thing up here. If this up here were like plus x squared, say, okay, no problem. I just make my rectangle a little bit longer. What goes in this top right box? What times what? What goes up there? What times what? This x squared gets multiplied by this x, right? So you just keep going down and across. Okay, so we have about 16 minutes for you to practice. Taking a look here at these first 3, only one of these is a lobster claw, even though they all look quite similar. Do you guys see the one that was the lobster claw? It's the third one. The lobster claw only comes in when it's parentheses times other parentheses. But this plus and this minus stuff we have done, this is old and it's here for a review, and also to make it clear, lobster claw doesn't just come in every time you see 2 parentheses. So give this a shot, raise a flag if I can help.